Hello and welcome to the video lecture of Numerical Integration Trapezoidal Rule. Outline of the lecture is Introduction, Trapezoidal Rule, Derivation of the Formula, Geometrical Interpretation by an Example, Composite Trapezoidal Rule, and finally some examples on Composite Trapezoidal Rule with calculator tricks. Introduction to the Numerical Integration. Numerical integration is simply the approximation of definite integral. But what is definite integral? Before that, what is indefinite integral? If we have a function x square, the indefinite integral is x cubed by 3, or the antiderivative of x square is x cubed by 3. In other words, in this indefinite integral, we find a function x cubed by 3 whose derivative is x square. And similarly, in general notation, we use small f of x for the given function, capital F of x for the value of the function that we want to find, whose derivative is small f of x. And now, in definite integral, we do the same, but also we use lower and upper limits. And this rule is called fundamental theorem of calculus, by which we find the definite value of the definite integral. In this case, that value is 20.33. But if we have a function like e power minus x square, we cannot find its antiderivative, or we cannot integrate it indefinitely or definitely, because there is no function whose derivative is e power minus x square. So this is the main issue, that we need numerical integration for such integrals. Also, integrals are used in the solution of differential equation. For example, indefinite integrals are used in solving first order separable ODEs, or also they are used in the second and higher order ODE solution. And the definite integral can be used to find the area under the graph of a curve, area between the curves, volume of solid of revolution, length of curves, center of mass, etc., etc. Okay, now come to numerical integration, which is the approximation of the definite integral. To approximate the definite integral of f of x from a to b, we use Lagrange interpolation formula. Let f of x is approximately equal to the nth Lagrange interpolating polynomial. So we just have to integrate this from a to b. And this formula number 1, is the general numerical integration formula for approximating f of x from a to b. And the derivatives, if we differentiate f of x, if we differentiate it and also differentiate the polynomial, in that case we called n plus 1 point formula for derivatives, for numerical derivatives. But this time we have a general numerical integration formula. In this general case, if we use n is equal to 1, we will have trapezoidal rule formula, or the formula that is derived from n is equal to 1. We also have another formula if we put n is equal to 2, and that is Simpson rule, but Simpson rule will be discussed in the next video lecture. This time we are discussing only trapezoidal rule. If n is equal to 1, k is equal to 0 and 1. If we put k is equal to 0, so we have f of x naught, L10 of x naught in the first term, if we expand the above summation, and this is the second term. By putting the values of Lagrange coefficients and using the simple integral of x minus constant, which is x minus c whole square by 2, use also x1 is equal to x naught plus h and fundamental theorem of calculus, and simplify. Here note that if we put x1, x is equal to x1, so this is 0, and similarly in the second term x is equal to x naught is 0 here, and the rest is very easy to calculate. So we have just derived the formula for n is equal to 1. This formula is called trapezoidal rule because this formula is also used for the area of trapezium or for the area of trapezoid. That's why we call this numerical integration formula as trapezoidal rule. Geometrically, we can see that as we have used P1 of x, first Lagrange interpolating polynomial for deriving trapezoidal rule. So we can see that our target is to find the area under the graph of a function, and for example the function is e power x, so area under the graph of e power x from -1 to 1 is this shaded region. This is required, but by trapezoidal rule we find the area under the graph of p1 of x from -1 to 1. So that's why there is a small error, and that's why we call the numerical integration as the approximation to the definite integral, because the main target is this exact area which is shaded, and we have found the area under the graph of p1 of x, which is of course more than this. Look at to this in the calculations. The integral of e power x from -1 to 1, we can use fundamental theorem of calculus, and we have e minus 1 over e. So this is the value, exact value. By trapezoidal rule, we can use f of x dx h by 2 f of a f of b. So the function is e power x, so we have e power a plus e power b, and so we have e plus 1 over e. Here the error is seen. We can also find this p1 of x for the given function and given x naught and x1, that p1 of x is equal to 1 over 2 e minus 1 over e into x plus e plus 1 over e. p1 of x, this is Lagrange, first Lagrange interpolating polynomial. So this is 3.0 something, which is the same as trapezoidal rule. And we can also see the trapezium or trapezoid in the figure, whose general formula is 1 over 2 height into base 1 plus base 2. If we rotate the trapezium in the above figure, so we will have a normal trapezium. Okay, we can also sketch the graph by using Desmos calculator online. Here, this is the graph of a e power x, and the bold graph is for e power x, and the other one is for p1 of x. For p1 of x, you have to write the polynomial p1 of x or p of x. It is easy if you write, for example, x square. Sorry, if you write x square, this is the graph. But this time we don't need x square. So this is how to see sketching on Desmos. Okay, next is a composite trapezoidal rule. To approximate the definite integral of f of x from a to b for large interval, the trapezoidal rule is not suitable. So we divide the interval ab into n subintervals. There are two reasons. One is that the interval is large, so the error will also be larger than the simple trapezoidal rule. The error in simple trapezoidal rule will be larger. So to reduce that error, even we can use composite trapezoidal rule for smaller interval to reduce the error. Or if we have a larger interval, in that case we must use composite trapezoidal rule. So what is composite trapezoidal rule? If we have a large interval AB and we want to divide into n subinterval, if we use n is equal to 1, this means that we have not divided this into subintervals. This is the original. AB is x0, x1, and we have the trapezoidal rule that we have already discussed. If n is equal to 2, we have to divide a, b, or x0, x2 into two subintervals and apply trapezoidal rule on each subinterval. On the first one, we have this. On the second one, we have this. So after simplifying, we have this formula for n is equal to 2. For n is equal to 3, we divide the given interval into three subintervals, then apply the trapezoidal rule to each subinterval. And adding, we have f of x naught plus 2 times f of x1, f of x2 plus f of x3. Similarly, for n is equal to itself, n can be even or odd. We can say that the integral f of x dx is f of x naught, which can also be written as f of a plus f of xn plus 2 times the sum of all f of x1, f of x2 up to f of xn minus 1. So this is the general formula for a composite trapezoidal rule. Before solving the example, let us recall equally spaced nodes. Let x0, x1, x2 up to xn are equally spaced nodes. What does it mean? This means that the space between x0 and x1, or the length between x0 x1 is h, the same length is between x1 and x2, and so on. So we can write a is equal to x0, x1 is equal to x0 plus h or a plus h, x2 is equal to a plus 2h, and xn is equal to a plus nh or x0 plus nh. So xn is equal to b, therefore we can write b is equal to a plus nh, or h is equal to b minus a by n, or n is equal to b minus a by h. If h is given, we can find n. If n is given, we can find h. Let us now solve some examples on composite trapezoidal rule. The first one is use the composite trapezoidal rule with n is equal to 4, 5, 6, 8, 10 to approximate the integral of e power x from minus 1 to 1. I have chosen this example because I want to compare the results with the trapezoidal rule, the normal trapezoidal rule, and here we will use composite trapezoidal rule. So for n is equal to 4, if a is equal to minus 1, b is equal to 1, h is equal to b minus a by n, which is 0.5. The general formula for composite trapezoidal rule becomes h by 2 f of x naught plus 2 times f of x1, f of x2, f of x3 plus this one. If we use the values x naught equal to minus 1, xn is equal to minus plus 1. Sorry, this is not minus 1, this is plus 1. This is just writing mistake. So here it is true. H is equal to 0.5, f of x is equal to e power x. We have this. Now here is the calculator trick. We have to use h is equal to 0.5, otherwise the trick will not work. So if we use h is equal to 0.5, and we also know that x1 is equal to x naught plus h, x2 is equal to x naught plus 2h, x3 is equal to x naught plus 3h. X naught is minus 1. So we have f of x1 f of x1 equal to e to the power minus 1 plus h, f of x2 e to the power minus 1 plus 2h, and similarly f of x3 is e to the power minus 1 plus 3h. What to do in the calculator? In the calculator, please use this command, e raised to the power minus 1 plus 0.5x. But in writing, you should use k or some other thing because there will be confusion if we use x in writing. So how to do this in calculator? I have a calculator on the screen here. Let us do it here. Please note that this is very important to learn this trick. 0.5 divided by 2 parenthesis, we have e to the power minus 1 plus e to the power plus 1, or simple e, but in between e minus 1 and e we have 2 times summation of the, what is the expression? The expression is e raised to the power minus 1 plus point k, minus 1 plus 0.5 k, but there is no k in calculator, so we write x from 1 up to 3. Press equal, and we have this result 2.39916. This is the result that is used by calculator. We can also find the exact value. This was already discussed by fundamental theorem of calculus in the example 1. Please look at the example 1 big. And the approximate value is this. So what is the error? This is the error. Now you can compare the error of trapezoidal rule with composite trapezoidal rule for n is equal to 4. The error is reduced. Now for n is equal to 5, h is equal to b minus a divided by n. That is, b is 1, a is minus 1. So 1 minus minus 1 is 2 by 5, which is 0.4. Now we have to replace the value of h and the value of n. N is 5. So how to do this? And the n is equal to 3. This will be replaced by 4. And here we will have 0.4. Go back, and here we will have 0.4 also. Equal. We have this result now by calculator. Now the absolute true error is 0.031. The error is further reduced. Similarly, if n is equal to 6, h is equal to 1 over 3, please write 1 over 3, 1 divided by 3 in calculator as I did above. Go back and forward in the calculator and use these values. We will have this result. The error is reduced further. For n is equal to 8, you can see that here the error is 0.02. Now the error is 0.012. For n is equal to 10, h is equal to 0.2, and the error is now 0.007. So this means that by using composite trapezoidal rule, we can reduce the error and we can have best accurate results. As we increase the value of n, we get the most accurate results. Now let us solve another example. Example 3. Use the composite trapezoidal rule with h is equal to 0.25 to approximate the integral of x ln x from 1 to 2. H is given here. So we have to find n, b minus a divided by h, which is 4. So n is 4. And here in the summation, n will be 3. x naught plus kh. H is 0.25, x naught is 1, so 1 plus 0.25k. Natural log of x naught plus kh. Okay, so by using calculator, we have this result. Now let us compare the result of trapezoidal rule. This is just directly the result. I have not used the formula, but directly written the calculation of trapezoidal rule. Look at this. In the composite trapezoidal rule, we have 0.6399, and here we have 0.693 something. While the exact value by calculator is this. Please also note that we can also find the exact value by calculator like this, the integral from 1 to 2 x ln x, x natural log of x, 0.63629. And so this is the exact value. By using this exact value, we can find the true error absolute true error and composite trapezoidal rule, which is 0.0036, and the absolute true error in the trapezoidal rule is 0.05. Example 4, approximate e power minus x square with h is equal to 0.1. As h is given, so we have to find n. N is 10. Use the formula as we did in the previous examples by using this summation. N is equal to 9 here. This is f of a and this is f of b. So this is the result. Note that if we use calculator for directly calculating this integral, this is not the exact integral. If we do this, e power minus x square from 1 to 2. Note that this is not the exact value as we have calculated this by calculator directly, but this is not the exact value. Why? Because we already know that there is no function whose derivative is e power minus x square. But calculator gives us this. This means that this is also some numerical integral value, but we don't know which numerical method is used in the calculator, is built in the calculator. So that was all for today's lecture. Next time, in the next lecture, I will discuss Simpson rule for n is equal to 2. First derive its formula and then use that formula to solve problems. Till that, bye bye and see you later.